Hello, everybody. So today we're going to talk about different types of chemical reactions. There's synthesis, there's decomposition, single replacement, double replacement, and then there's some other extra ones, some special conditions, such as endothermic, exothermic, incomplete combustion, complete combustion, and chemiluminescence. So we're going to go ahead and start with the four most common types: the synthesis, the decomposition, the single replacement, and the double replacement reactions. So for a synthesis reaction, it's probably what you might think it is, where you basically just take some things together and you join them. You synthesize something. So let's say you were going to take the element hydrogen and you were going to join it with the element oxygen. What you would end up making is water. Now you might be wondering, well, why don't we just write down an H and why don't we just write down an O? And the reason why we don't do that is these are referred to as diatomic atoms. Whenever you have certain elements, and there's only 7 of them, and those elements are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you have any of those elements by themselves, they usually will link up to one another and bond covalently just in the air, and so they typically will be shown with a little 2 after them. Any of the other elements on the periodic table, you're safe to just write the element, by itself with no subscript of the 2. If it happens to be one of those 7, you want to go ahead and include that 2 after it. So this is a synthesis reaction. So if you look at the pattern, what you're doing is you're taking more than one element and you're making one compound. So that's the key thing that I tell my students to look for, is that you're looking for one compound. In a decomposition reaction, you're doing the exact opposite. You're taking one thing and you're breaking it apart into multiple. So for example, you could take the compound sodium chloride, NaCl, just table salt. And if you put an arrow after it, you can break it down into its individual elements. You could break it down into sodium, and you could break it down into another element, chlorine. Now, if you notice, chlorine is one of these diatomic elements. So I'm going to go ahead and put a little 2 after it. Okay. And then and again, you have one compound that you're starting with. And so that's the pattern that you want to look for. And it doesn't have to just break down into 2 things. It can break down into 3 or 4. And then the same thing for the synthesis reaction. It doesn't really have to just start with 2 elements making one compound. You could start with an element and a compound making one compound. You could maybe start with 2 compounds making a single compound. The key is you just have, for a synthesis reaction, one compound after the arrow. In a decomposition reaction, you have one compound before the arrow. In a single replacement, what you have is you start off with an element in a compound and you break it down into 2 new elements and compounds. So for example, if we take the element copper, we could react that with a compound such as HCl, hydrochloric acid. And when we join those things together, what will happen is you'll end up making Cu with the Cl, and then the H will be up by itself. And I'll explain to you why the certain elements, why does the Cu switch with the H and why does it not switch with the Cu. So let's just go ahead and just do the switch. So the H is going to be here. Notice that H is one of these diatomic things, and we wrote it by itself. So we have to put a little 2 there. And then the Cu is going to join with the Cl. And the actual formula for this is CuCl2. And if you're wondering, like, well, how does he know that there's a 2 after that Cl? Is it because of what's up here? And no, that's not it at all. If you remember one of the previous lessons, I talked about how you figure out the charge on an anion. And so if you take a look at where Cl is located, Cl is over here. And we would label this as a 0, and this is a -1, and this is a -2, and a -3. Chlorine is going to have a -1 charge. And if you look where copper isn't in a strange area of the periodic table. It's where the transition elements are located. And these guys can have different valences. And as a result, they can have different charges. So copper, if you were to look it up, can either have a +1 or a +2 charge. And usually copper has in a compound a +2 charge. So that's just something you wouldn't really be able to figure out. That's something you would have to know. And so if we gave you a problem like that on a test or a quiz, we will give you what's called an ion sheet showing you what the charge is for the transition elements, so you would know which ones to use. Okay. So let's take a look. So yes, if you look, you have an element with a compound, and you make another element with a compound. So that's your pattern there, is that you have an element, a compound in the reactants, and we call the things over here the reactants. And over here in the products, you have the same type of thing. You have an element and a compound as well. Now you can write them in any order that you want. You don't have to write the Cu first. It could have been HCl plus Cu, and that would be fine. And then an arrow, and then CuCl2 could be here, and H2 could be after the plus sign. It doesn't really matter the order as long as on the left side of the equation you have an element and a compound, and on the right side you also have an element and you have a compound as well. How about double replacement reactions? In a double replacement reaction, notice the key word here is single, and it's replacement. So you have two elements that trade places and switch. In a double replacement, you have two compounds of which two elements switch. Okay? And typically the things that do the switching, like for the first one, the copper is going to switch with the hydrogen. Why does that happen? And the reason why is because when you look on the periodic table where they're located, hydrogen is over here in the metals region, and copper is over here in the metals region. Remember, you've got a staircase that zigzags down through the elements like this. It separates the metals from the non-metals. And since both of these elements are in the metals region, they're going to be the ones that trade places. They end up swapping. So hydrogen is now over here where copper was by itself. And again, it's diatomic substitute. And the copper is going to be over here with the Cl. Right? So for a double replacement, same kind of thing happens as a single replacement, but you have these two different compounds that do that switching. So let's say you're going to take the compound AgNO3. And maybe you're going to react that with salt water. This is actually a common test that is done to see if you have, if you actually have too much salt in your water supply, too much sodium. What will happen is, a technician can come out, especially if you have a well, they can add a couple drops of this silver nitrate solution, and what will happen is it will precipitate out and form a white precipitate with a sodium ion, and it gives them an indication that you got too much salt in the water. And then you might have to put some kind of filtration system on it. Okay, but anyways, so the same type of idea is going to happen. We're going to take the two metals, because they're like one another, and we're going to go ahead and switch their places. So Na is now going to be in the front here with the NO3, and the Ag is going to be over here in the end with the Cl. And again, at some other point in time in the future, we'll go through a lesson where we can show you how you figure out what these numbers are going to be. But in general, if you take a look, you can kind of see what really happened here. The Ag and the Na simply swap partners from one another. And so you have a compound reacting with a compound, making a new compound, and then also a second new compound. So those are the patterns you look for in different types of chemical reactions. You make one compound, it's synthesis. You take one compound, you break it apart, it's decomposition. If you have an element in a compound, and you make another element in a compound, that's an example of a single replacement reaction. In a double replacement reaction, you have four compounds, two in the reactants, and then two in the products. Now, we can also do some balancing with these too, because usually that's what we do, and we'll use things called coefficients to do the balancing. I believe that we have that in another future video, but I'll give you a preview of that. If you notice that there's only two Cl's here, there's only one Cl there. The key to balancing is that you want to put whole numbers. You can only use whole numbers. So when you're balancing, You only want to use whole numbers, and we call those coefficients. And there's a rule, you can only put them in front of things. And they basically act as a multiplier. So for example, and the reason why we balance this is because we want to follow what's called conservation of mass. You can't destroy matter. You can't really create it. You just can only rearrange it. And that's really what conservation of matter means. And so that's really what's going on in an equation. In the reactants part, you're joining stuff together. That's what you're starting with. That's your beginning part. And then your ending part is over here. You still have to have the same elements there. And you really should have the same number. And if you don't have the same number, you have to balance to fix it. So if we look at the first one here, there's two O's here, and there's only one O here. There's no number written after the oxygen, which means you have one of them. So what can you do? You can put a number in the front here, you can put a whole number here, or you can put a whole number here. You can't split up a compound, but you can put it in the front. So you could take that 1 and multiply it by 2, and now you've got your 2 oxygens. So you have that fixed. But in the process, you just messed up the hydrogens. So, because you have to multiply those as well. 2 times the 2 here gives you 4 hydrogens. So you would have to put a 2 there so that you end up having 4 hydrogens over here as well. And when you put a 2 in front of something, what you're really doing is you're really just doubling it. So it's like instead of writing water once, you're just writing it twice. So if you count them up, you got 4 hydrogens here and 2 oxygens there. And the same thing here, when you put the 2 in front, what you're really doing is you're just writing that hydrogen twice. So you basically got 2 plus 2 gives you 4 hydrogens there. All right. We can do the same thing for balancing here. Again, you can only put numbers here, here, or here. You've got a 2 after the Cl. You've got a 1 after the Cl. So you would have to multiply that one by the whole number, 2. And then you have to fix the sodiums now, because now you've got 2 of those. 2 times the 1 here is 2 sodiums. And that's how you would go ahead and fix it. And again, if you don't like that method, you can think of it this way. When you put a 2 here, you really have NaCl written twice. So you've got 2 Cls and 2 Nas. And the same thing here, when you put a 2 here, it just means that you have 2 Nas written twice. That's all it really means. Okay, single replacement. This one also needs to be fixed. There's 2 hydrogens here, and there's only 1 here. So we would have to multiply through by a 2. And then here you've got 2 Cls and only, well, now you have 2 Cls because you just fixed it. Isn't that great? 2 times the 1 gives you 2 Cls. And that matches the 2 over here, and it's balanced for you. And then for this double replacement reaction, actually everything is already balanced. We have 1 Ag, we have 1 Ag, 1 N, 1 N, 3 Os, 3 Os, 1 Na, 1 Na, and 1 Cl, and 1 Cl. So we're okay there. So those are your 4 main types of different chemical reactions. But we also do have some other types that occur from time to time. And endo and exo are probably the most common ones. In fact, you could classify any of these reactions as endo and exothermic, because every reaction will either release a small amount of energy or it will absorb a small amount of energy from its environment to get started. Sometimes it's not measurable, but you really could classify just about any reaction as endo or exo. And so in chemistry, we really only show the students the ones that are really obvious, where you do get a temperature change, where something goes up, or the temperature change goes down. Okay, so let's talk about those first. So there are some other types of reactions. And those other types of reactions we can say are endothermic, which means that energy is absorbed to start that reaction. Because energy is being absorbed from the surrounding, what happens is the environment feels cold. Because there's an absence of energy. It's going into the reaction to get it going. In an exothermic reaction, you have just the opposite going on. You have energy that is released. So as a result, you would expect what you think is going to happen. What you think is going to happen. The environment around where that reaction is occurring is going to get hot. So how do you signify whether something's endo or exothermic? Well, you could take, for example, um, zinc metal, and you could react it with hydrochloric acid. So we'll do a single replacement reaction here, but where it is actually, no, this wouldn't be a good endothermic one. This would be a good exothermic one. So if you take zinc and you react it with HCl, you're going to get H2, and you're going to get ZnCl2. Now, you might be like, well, how do you know if it's exothermic? Because what will happen is you'll also see written in the equation the word heat, or sometimes they use the word energy over here. And that indicates that energy was released from the reaction since it's in the products, and that would be exothermic. If it's an endothermic reaction, you would see something else where you would actually have the heat being written in the reactants. And a good example of that would be that you could take a compound called ammonium nitrate, and whenever you dissolve that into water, what happens is it will end up producing ammonium ions and nitrate ions. And in that process, this is really like a decomposition reaction, except you have heat that actually is absorbed to get this reaction to go, and the environment actually feels cold in that process. So that's an endothermic reaction. You would simply just look to see where the word heat appears. It's in the reactants. Endothermic, if heat is in the products, it's exothermic. Now, another one that I think is really cool is where sometimes you don't have heat energy that's produced from a chemical reaction. Instead, you get another type of energy. Sometimes you get light energy that's produced, and that is called chemiluminescence. So an example would be like, what you see in a firefly's tail. In the abdomen, there are two chemicals that are secreted that the male secretes that causes that pulsing yellowish green glow that basically attracts the female for the mating process. In some areas of the ocean, there are fish that actually glow, so that way there's enough visible light down there, so that way they can maneuver and they can actually see. I mean, I'm talking about depths of the ocean where it might be like 8 or 9 miles deep, so really, really deep areas like maybe in the Pacific Ocean or maybe in the Atlantic. All right, so let's talk about chemiluminescence. So an example of that would be you can take this compound called luminol, and I'm not going to write the chemical formula version of it. I'm just going to go ahead and write a word equation for it, which just means you're using words instead of the symbols. So if you take a compound called luminol, and I'm going to demonstrate this later for you guys. If you take a compound called luminol and you react it with another compound called potassium ferrocyanide, what you'll end up doing is you'll end up producing a version of luminol, and you'll end up getting some hydrogen gas. And I can't remember exactly what the compound is called, so I'm just going to go ahead and write the word compound here. And what happens is that compound will be emitting light. And so as a result, typically what you will see if something's a chemiluminescence reaction is that they'll put the actual chemical formula, or they'll do it like this, write the word for it, and they'll put a little asterisk above it, which just means that substance is emitting light in that process, which is really cool. And you get like this blue kind of color that's emitted from this type of reaction. So that's a chemiluminescence reaction. Another type is a combustion reaction. There's really two types of combustion reactions. So there's complete combustion, where in a complete combustion reaction, you take something like maybe gasoline, And that's the formula for octane or gasoline, which is the major ingredient in gasoline. Gasoline is really a mixture. It's got other additives added to it, but this is the main component of it. If you react that with oxygen, what you'll end up producing is carbon dioxide, and you'll end up also producing water in the process. If it's incomplete combustion, what you have ending up occurring is if we had C8H18 reacting with oxygen, there isn't enough of oxygen available to completely burn all of this fuel. So what happens is you end up getting some kind of smaller compound other than CO2, which is carbon dioxide. What's smaller than that? It's probably in your house that is dangerous, and you usually have detectors for it. Well, one of those is carbon monoxide, and that's an invisible gas, just like carbon dioxide. But what happens is it competes for the oxygen in the red blood cells more than oxygen itself. And when it binds to the hemoglobin molecule, it doesn't allow your own red blood cells to grab onto oxygen. So you actually kind of suffocate at a molecular level. Kind of a nasty way to die. What happens first is your brain shuts down, and then your body starts shutting down afterwards. Another one is that you might not have CO or carbon monoxide that's produced, but maybe there's even still not enough of oxygen available. There's only enough of oxygen to maybe make water molecules. You could just get plain carbon in water. And the dead giveaway for this is a black kind of smoky substance. So like when you first start a fire, for example, when you first start a fire, it ends up looking kind of like black and sooty. You've seen soot before, and then as it gets hot, it's able to draw more oxygen into the fire, and it switches over to complete combustion. So when you first start a fire, like outside, like if you're camping or in your fireplace at your house or wherever, maybe in your grill, if you're using charcoal, it smokes a lot at first, and that's because you got incomplete combustion here. It's not hot enough to draw enough of oxygen in to completely burn it. But in complete combustion, you are drawing in. Now the flame is really hot, the fire is really hot, it's drawing in enough of oxygen, and you make a larger molecule, you make carbon dioxide, and you make water. So those are really the 5 other types of chemical reactions. Now to balance these guys, it's pretty challenging because they're usually involving big fuels. This fuel sometimes is referred to as a hydrocarbon, meaning it's a compound containing hydrogen carbon, and it's just simply a fuel in common words. But basically what happens is that you're going to need large amounts of these materials to get this compound, because it's usually pretty big in size, to balance out. And usually I follow something called, I know this is funny, it's called Cookie's rule. Years ago I had this student that realized a pattern, and she said that 50% of the time when you do a complete combustion reaction, you're going to need to stick a 2 here to get it to work out. So why not just always put a 2 there, all right? And so if we do that, we put a 2 here, we'll end up with 16 carbons. So we put a 16 there because there's only 1 here now. Now we've got 16. But in the process, we mess up the O's. We got 32, but we'll come back to those. And 2 times 18 gives you 36. Well, 2 times 18 would give us 36. And now we've got the hydrogen, the carbon fixed, and we've got to fix the oxygen. Be careful, because the oxygen is here, and you've got 32 of them. And the oxygen is here, and you've got 18 of them. And when you add 32 and 18 together, you end up with 50. So we really need to have 50 O's over here. Well, 2 times what gives you 50? And that would be 25. So as you can see, if you put a 1 here, or you didn't put anything there, this would be like 12 and a half. And you can't have like half of a molecule or half of an atom, all right? You got to have the whole thing, or you don't have any of it. Sometimes in incomplete combustion reactions, you also need to put a 2 there, but not always. So you could just try balancing it without putting a 2 there. And if you ran into difficulty, then I would recommend putting a 2 here and then go through it. Just follow Cookie's rule. And that was her nickname, which is why I call it Cookie's rule. And that's how you would go ahead and balance an incomplete combustion reaction. So those are really, I've gone over 9 different types of chemical reactions. There's 5 other types, which are these, and then you've got the 4 main types, which are the synthesis, the decomposition, the single replacement, and the double replacement reactions. So that's basically it. Those are chemical reactions. I know I went into a little bit further than probably what was needed to, but I know that some of the other videos talk about balancing as well, but I just wanted to go ahead and go through that with you. Sometimes it helps to see it a second different way. If you haven't done balancing, maybe you like my method better. Maybe you prefer one of the other videos. And it's up to you, whatever you want to use, as long as you get through the goal of being able to balance chemical reactions. And stay tuned. I'm going to do some demonstrations as well, and I'll post those also online for you to see that demonstrate the different types of reactions that we have here, and some of the other types on the other pages as well. All right, take care, everybody. Stay safe. Bye.